Welcome back to Physics 141 Online. As we move into Chapter 9 in the textbook, we're going to move into a section where, rather than concentrating on the motion of a single particle, or perhaps two particles that are connected by a string so that their motion is constrained in some way, we want to be able to analyze the behavior of systems of particles, two or more particles that may collide or interact with one another in some way. And we want to be able to understand how they both move in these situations. So we'll begin with the definition of the center of mass of a system of particles. Here's the way it works. Imagine we have three particles. We could have more, but three particles that are sitting at different positions in the xy plane, and they of course have different masses, or they could at least in principle have different masses. We can define the position of the x and y coordinates of the center of mass by taking each coordinate, each x coordinate, and multiplying by the mass. And so if we do this for all the particles in the system, which amounts to summing up this quantity m sub I times x sub I, and then dividing by the total mass, that gives us the x coordinate of the center of mass. And we can do the same thing for the y coordinate. So if we do this procedure twice, we will then find the location of the center of mass because we will know its x and y coordinates. Clearly, as you can see, the more massive a particle is, the greater influence its position has on the center of mass of the system. And I hope that this summation notation is familiar enough to you. We've been using it when adding up the sum of forces on an object, so here we just have a different kind of sum. We can write this in vector notation a little bit more compactly because r is the general symbol for a position vector. So r is equal to x times I hat plus y times j hat for a particular object. Here we combine the x and the y coordinates into this vector notation so that if we know the position r sub I of particle number I and multiply by the mass, we sum that up and divide by the total mass, and that gives us the position of the center of mass. We just have to remember, of course, that in this sum the r values are vectors so that they have an I and a j and perhaps a k component if we have objects that are at different positions in three-dimensional space. So the position vector then, just to remind us, is given by, for a single particle, is given by xi plus y times j. And the reason that we like this vector notation is that we now can define both the velocity and the acceleration of the center of mass of a system of particles. All right, instead of using x and y separately, we can now use vector notation to express the velocity of the center of mass as the time derivative of the position. And so if we go back to the definition of the position of the center of mass, that was the sum of m sub I times r sub I. Well, when we differentiate each of those terms, we end up with a velocity. And so the velocity of the center of mass is the mass times the velocity of each individual particle, all added together, divided by the total mass. And by analogy, we can do the same thing with acceleration. Acceleration of the center of mass is the derivative of the velocity of the center of mass. And when we differentiate each of the terms in this summation, which is the expression for the velocity of the center of mass, we get the acceleration of each particle. So mass times acceleration for each particle summed up, divided by the total mass of the system, is the acceleration of the center of mass. But wait, look at this summation. The sum of m sub I times a sub I, well, m times a for a given particle is equal to the total force that that particle experiences. So the acceleration of the center of mass is the sum of all the forces on all the particles in the entire system divided by m. And we can rearrange this and write this down as Newton's second law for the entire system. We can solve this for the sum of the forces and realize that it's going to be the mass times the acceleration of the center of mass. All right, so we take these two terms, set them equal to each other, rearrange by solving for the sum of the forces, and we get this very familiar looking equation, but realize it means something different now. We're not talking about a single particle, rather a system of I particles, where we have I goes from 1 to some maximum value of n. And so the sum of all the forces on all the particles is not equal to any of their individual masses, but the sum of all their masses times the acceleration of the center of mass. And this has profound consequences, as we'll see in just a minute. our next step in analyzing the motion of a system of particles is to realize that there are two types of forces that act on those particles. One type of force would be what we call an internal force. That would be a force that one particle in the system exerts on another particle in the system. They might collide with each other, for example, and exert forces for a short time while they're in contact. But then there's also external forces. If the whole system of particles is acted upon by something from outside, for example, the Earth, pulling on that entire system of particles, that would be an external force. So we can take this summation and break it apart into two sums. One that would be the sum of the forces on all of the particles due to external forces, and then the sum of the forces on all the particles due to internal forces, forces that they exert on one another. And the reason we do this is we remember Newton's third law says if particle 1 acts on particle 2 with a force, then particle 2 acts on particle 1 with the same force in the opposite direction. And that means that all of these internal forces are composed of terms that cancel out with another internal force. And as a result, that summation of all the internal forces adds up to 0. So what we're left with is a simpler expression that says, here's your system, define your system and identify all the particles that are in it, add up all the forces on those particles, not that they exert on each other, but only the forces that are exerted by something outside the system. And the sum of all those forces becomes the net force, and that's equal to the mass times the center of mass acceleration. Now what does this mean? It means that the center of mass of a system of particles behaves exactly the way that a single particle would if it had the total mass m and if it were subject to the same external forces that all the particles in the system feel. And this is helpful in analyzing the motion of extended objects. For example, if I took a baseball bat and I threw it in the air, and that baseball bat was spinning as it was moving through the air, I could analyze the motion of that baseball bat by focusing on the center of mass. And so if I knew where the center of mass was, if I could label it by putting a mark on the baseball bat where the center of mass was, as it flew through the air, the center of mass position would be the same as a particle that had the entire mass of the baseball bat located at just that point, the center of mass. And that means the center of mass of any object, like that baseball bat flying through the air, would trace out a parabolic path, the same that we're familiar with projectile motion. And so that's very significant. So what we can deduce from this fact is that if we have an isolated system, now my baseball bat flying through the air is acted upon by the Earth, and so there is an external force acting on that baseball bat. But imagine I threw the baseball bat into space somehow, if we took it out of the space shuttle and just released it. Now it's tumbling through space, but there's no external force acting on it because it's too far away from any nearby planets or moons for that force to be significant. So that's what's called an isolated system. If the external forces on that system add up to be 0, then we know that the mass times the acceleration equals 0. And since we know the mass isn't 0, that means the acceleration is 0 for an isolated system. Therefore, for an isolated system, the center of mass velocity is a constant. And that's significant. This is very helpful in characterizing the motion of an isolated system. Very special case is the one in which that system is initially at rest. So if the whole system is at rest, the center of mass must be at rest. And what that means is, for that kind of a system, the position of the center of mass will always be a constant. And I'll just give a quick example that some of you might be familiar with. Imagine that you're in a boat and you are near the dock and you're trying to get out of the boat and climb up onto the surface of the dock. Well, as you do that, if the boat is initially at rest, as you step in one direction, then the center of mass of the system, its position has to stay constant. So what happens in response to your motion is that the boat goes off in the other direction. And so that situation can be analyzed quite simply using this principle here. That if you have a system where the center of mass is initially at rest and there's no external forces that act on it, that means the center of mass position stays constant, and we can solve problems that way. I'm going to skip over this example problem and do it in class, but go on to the next section that takes what we've learned so far about the center of mass and shows how it implies a very fundamental principle of isolated systems. So another way that we can take the equations that we've already used about an isolated system, we can write them down to say that for an isolated system the net force is 0, therefore the acceleration is 0, which means the center of mass velocity is a constant. So going back to the definition, the center of mass velocity is this sum of m sub I times v sub I over the mass of the system. So m times v center of mass, if we multiply both sides by m, we see that mv center of mass, which is the sum of mv for all the particles in the system, that is equal to a constant. And that's interesting. When physicists find a quantity in their equations that's predicted to be a constant, they often attach special importance to it and sometimes even give it a definition. This is what lies behind all kinds of what we call conservation laws or conservation principles. So we give a special name to this product, m sub I times v sub I. In fact, for a given particle, that product we call the linear momentum of the particle. So p sub I is just the symbol that we give to define that product. And what this means is that we can write down the law of conservation of momentum for a system of particles, because we know that no matter what happens as the particles move, we know that the velocity of their center of mass stays constant. And because now we've defined this momentum, we can add up the momenta. We can add up these m sub I, v sub I terms for all the particles in the system, and whatever they are at an initial point in time, they have to stay that way all throughout subsequent time. So pick an initial situation, add up this quantity, and then perhaps these particles collide or they interact in some way, and then some final situation prevails a little bit later. Well, we have the same thing at the end as we do at the beginning. So this principle, this equation, I put in a box, a colored box, because it becomes the starting point for the analysis of all kinds of colliding particle systems, as long as those systems are truly isolated and there's no net external force acting on them. Just remember though, just as in the case of force, when we write down one of these sums, remember that momentum is a vector. Because of the way we've defined it, it's the product of mass and velocity. And so these equations here could potentially have I and j and even k components to them. And we would have to consider all of those in order to apply this equation correctly. So let's just do a very brief survey of the different types of collisions that we're going to encounter in this chapter. The law of conservation of momentum is especially helpful in analyzing those kinds of interactions in an isolated system because we don't have to know anything about the forces. The collisions that happen are often very complicated things, and we don't really need to know any information about them other than the fact that here are these particles, they collide, they interact, and then afterwards they do something. All we have to really know about is what happens before and after, and then we can analyze what was going on initially. So before we work out some examples of these collisions, we usually define collisions into two major types, and the first is a matter of elastic collisions. For both elastic and inelastic collisions, the total momentum of the system is conserved, and so that's not the question here. The reason these two differ is because in elastic collisions, the total kinetic energy of the system is the same before and after the collision. What that means is there's no energy that's lost in the collision, hence the objects that are involved must be elastic. If they deform a little bit the way a spring might, then when they return to their original shape, all of the energy that went into the deformation comes back. None of it is lost. Inelastic collisions, by contrast, are collisions where the total kinetic energy is less after the collision than it was before. And this is because some energy is lost in the process. These objects, indeed, are not truly elastic. And a good example of this might be a collision between two cars. Automobiles are made of materials that usually deform, and when they deform, energy is lost. The metal or the plastic breaks, Energy is released in the form of heat and noise, and these collisions are those where total kinetic energy is not conserved. There's some type of non-conservative work that's being done. So those are the two categories that all collisions fall into, one or the other. And of inelastic collisions, those where kinetic energy is lost, there is one special type, and we will focus on this in some of our homework problems, and that's a completely inelastic collision, which is a collision where objects not only collide, but they stick together after the collision and move together. And you can imagine two lumps of clay, perhaps, that are launched toward one another, and they collide with such force that they stick together, and then they go off together. And that kind of a collision, a totally inelastic collision or completely inelastic collision, is an easy one to analyze because after the collision's over, there's only one particle. So it makes keeping track of the momentum a little bit easier. And an example of an inelastic collision in reverse might be something that explodes. Imagine that you have a hand grenade that's thrown into the air. It's a single particle, then it explodes, and it's broken up into thousands of tiny bits. Well, this is exactly what you would see if you took an inelastic collision and ran it in reverse. And so we can analyze it the same way. If an object breaks into a number of smaller pieces, all we have to do is add up the momenta of the different pieces and set them equal to the momentum of the initial particle, and that will allow us to get information about that collision. We'll learn a lot more about these as we do examples in class, so I hope this is a helpful introduction. I'll see you in class.